recording. You're so quick. All right. So, like I said last class, so I'm going to be dropping your lowest 2 assignment grades, right? And so I am going to give you this assignment 6, which is on proportions, and then I'm going to give you another assignment 7, which is just a quick one on regression. Okay. But it's unfortunately going to be quick turnaround because I want to get it in on Wednesday, which is our last class. And so just keep that in mind. Okay, we're hopefully going to start chapter 7 today. Give you what you need, nothing that you don't. And then we'll do review on Wednesday. Okay. So I haven't heard anything, but I also haven't checked in a long time. So you would think that they would let me know, but I don't, sometimes they don't. Okay, so thanks for doing my evaluation. That was great. Just a heads up that lab on Friday is uncanceled. Yeah. If you're planning on coming to one of those many office hours that I'm offering, that's fine. I sent out an email last night. So lab on Friday is uncanceled. I'll be there, I'll be available. We can work through your lab report. Okay. I also posted a sample lab report, right, with the code so you can kind of know what I'm expecting to see, right? And then you can see the code that I used to get there, right? Kind of reverse engineer it, if you will. Okay. So, all right. So today we're going to do 6.2, and assignment 6 is going to be a little bit shorter because, well, maybe I should kind of ask you guys, would you prefer to do hypothesis testing, like formal hypothesis testing, find the p-value, all that fun stuff, or just use the confidence interval? Because we're only going to do one. Uh-oh. It's like formal. I was going to just do the confidence interval just because it's a little bit easier, right? And so we'll just do a confidence interval for 2 proportions, for testing if 2 proportions are the same or are they different or is one lesser, whatever. Everywhere.
Our final date hasn't changed.
Oh, perfect. So it's on the 12th, right, at 6? Yeah, okay.
Whatever it was.
Whatever it was, it still is. Yeah, cool. Awesome. So let's do, so 6.2 is, don't really have time to review 6.1, but on the plus side, 6.2 is just a bigger version of 6.1, so it is going to be a review. Okay. And I'm so confident in you guys and your hypothesis testing abilities that even though we're not going to talk about it, given the formula sheet, you could do a formal hypothesis test of 2 proportions, right? So what's the proportion of males born in Penticton versus the proportion of males born in Kelowna? Is there a difference? Right? You could, given the information, answer that hypothesis test. Okay? But like I said, we're just going to do these with a confidence interval. Move on. Okay? So 2 proportions or 2 sample proportions. we will only look at confidence intervals to test hypotheses. Which means you don't have to do 2B on the assignment. Exactly. So not doing 2B on the assignment. Yes. What a great idea. But if you do it, I'll make all 7 marks available for bonus marks. How's that for tempting? Huh? But if you do it, you could get all 7 marks as bonus marks. Star eye emoji. How's that sound? That's pretty good. Okay, so if you give it a go, I think that if you can pull it off, then you are worth those 7 extra bonus marks on this assignment. Okay, so for proportions, let's just read that example that we have. Let's start from the example because we have a general idea of how proportions work now, right? We've got some count and some category that we want to compare to. In the 1 sample case, just the number, right? In the 2 sample case, now we have 2 counts in the same categories, but from different groups, right? And we want to compare those counts. Are they the same or are they different? Right? And so we'll start with our assumptions, but we'll steal this example. So we'll kind of work through it by example. Okay. For confidence intervals, the assumptions are going to stay the same. You just have to check them for both groups. That's all. There were a lot of assumptions that we had to check for the 1 sample proportions, right? We have to make sure that we have a random sample, right? We have to make sure that our sample size is less than 10% of the population just to preserve independence, okay? We have to make sure that we have, for confidence intervals, that we have at least 10 successes and 10 failures. So now we have to check that for both groups, right? And then finally, because we're comparing 2 groups, these have to be independent groups. I'll just kind of gloss over that. It's kind of obvious that they have to be different groups in order to compare them, right? So, oh, you know what? I guess I should have, oh well. I'll copy it later. So, a surprising number of young adults, ages 19 to 25, still live in their parents' home. Yes. I live in my parents' condo. They don't live there, but I guess I'm one of them. And I'm 32, so. A random sample by the National Institutes of Health included 2,253 men and 2,629 women. Right. So those are your total sample sizes in their age group, or in this age group. The survey found that 986 of the men, right? So now you've got a proportion of men, and 923 of the women, right? So you've got a proportion of women live with their parents. Okay. So proportions questions are the easiest to identify because I don't give you a mean and I don't give you a standard deviation. So if you read a question and you're kind of thinking, oh, where's all this information that I need? Well, it's probably a proportion question. But also, well, if I ask you to check the assumptions, it's for sure a proportion question. But even in the question, I have to say the word proportion at some point, right? So test the proportion, whatever, okay? So there's lots of clues going on in here that tell us that, hey, we have a proportion question. Right? And as you noticed for assignment 5, where I made you identify the type of questions, right? It can be tricky, right? And so that's why I want to prepare you for the final where you're reading all these questions, and if you're not sure which type it is, right, then how are you going to know where to zoom in on your formula sheet, right? So I'd say the hardest part is reading a question and figuring out what type of question it is. Once you know, then that's it, you've locked it in. Right? So for our assumptions, so assumptions for 2 sample proportions, are as follows. Remember, we've got 2 sample sizes, right? For men and for women. Right? And so we've got the N, how am I going to number these? 1. Both samples must be random. Let's check here. Hey, a random sample by the National Institutes of Health. Great, right? Both these samples were selected randomly. Or they're 1 sample and they've been split into male-female groups, doesn't matter. So I'll just say here, for our case, sample was randomly selected. Because it says that. The second assumption, right, is that N1 has to be less than 10% of the population. And N2 has to be less than 10% of the population. Yeah. Like I said last day, so all these assumptions will be met, or we have to assume them, right? That's the idea with assumptions, right? So even if it's not obvious, we say, okay, well, I'm assuming that the group of males that I've collected and the groups of females, they're both less than 10% of the overall young adults. I'm guessing in the States. Okay. But it's reasonable to assume that 2,253, less than 10% of all young adult males. Right? So we say something like, it is reasonable to assume N1 equal to 2,253 is less than 10% of all young adult males. ditto for females, right? But, oops, it's got messy. I'll just add n equal to 2,629. Is less than 10% of all young adult females. So you're just going to argue that, yeah, this is less than 10%. We talked about this last day. Why do we have to have less than 10%? We know big samples are good, right? But because we need each individual to be independent of the other, if you've got too much of the population in there, right, you're going to have siblings in there, you're going to have people in the same family, people at the same school, you're going to have making room for non-independent observations, right? Kind of groupthink, if you will. Okay. So that's why we have to check that we have less than 10% of the population. Just so if you argue it here, that's all you need. If you can't remember what they are, at least if you can jot down, okay, well, they have to be random, and I know the sample size has to be less than 10%. So even if you can't make the connection between arguing for this particular example and the general one, I'll accept just the general conditions for just a few less marks. Because I know it's crunch time and you're all just memorizing this anyways. So the important part is when you're out in the real world that you remember that you have to check the assumptions. You can look them up later, right? That's not the hard part. It's just remembering that that's something that you have to do. So just the light blue for full marks and just the dark blue for par marks if you want. If that makes sense. So for confidence intervals, we had to check that the number of successes, right, which mathematically is N1 P1 hat, has to be greater than 10, right? So more than 10 successes in group 1. We also have to check that N1 Q1 hat is greater than 10. So we have to have more than 10 failures in each group. Right? So now we're just doubling up, right? Because this was the condition for confidence intervals for one sample proportions. And now we have to check it for both groups, but they stay the same. So more than 10 failures in group 1. So either you know the number of successes, right? In this case we do, right? You know that the number of successes for the male group is 986, right? 986 is larger than 10, right? And that's 986 out of 2,253 men, right? So the remainder is the number of failures, right? If you're not a success, then you're a failure. Clear as day, guys. So, if you want, you can just steal the number of successes. So for group 1, let's say that's the males, the number of successes is what do we say? 986, which is greater than 10. I just put a little check mark after. The number of failures is 2,253 minus 986. 12,067, which is greater than 10, check mark. Got a little cram there. Like I said, all these conditions, they're gonna check out one way or another. Right? We just have to know to check them. Okay. If you have the proportion, right, you can use the sample proportion and multiply it by the overall sample size, right, to get these successes and failures. But sometimes I think it's easier to just grab the number of successes if you have them, figure out how many failures there were. Are they greater than 10? Yes, they are. Great. Okay. We also have to check that N2 Q or P, skipping straight to Q. P2 hat has to be greater than 10. It's the same condition, right? Remember, Q hat is 1 minus P hat. Q naught is 1 minus P naught. Q is 1 minus P. So more than 10 successes in group 2. And we also have to have more than 10 failures. More than 10 failures in group 2. Oops. Group 2, let's make that the females. Number of successes, right? If you said you live with your parents, then you're considered a success, right? So 923. 923 is greater than 10. Great. Number of failures is the total sample size of the females, 2629 minus 923. They're out living on their own, being failures. 1,706 of them, also greater than 10. Because we're not doing the hypothesis test, we're not going to talk about the assumptions because they get a little involved, but it's only for the formal hypothesis test. So we're skipping over it. Okay. So, any questions about these assumptions? So for confidence intervals, they just stay the same. Now you're just checking for both samples. So that's nice. Feeling ready? I guess we're not doing this one. Not doing. Because we said we're only going to test using confidence intervals. I was prepared to go through it. And it's so funny because I know that the person who teaches this course or has in the past, she's like, oh no, I only do confidence intervals for proportions. I was like, oh no, we'll do both. It's fine. But now I'm like, should have just done confidence intervals. Oh well. So we're gonna see, is there evidence that there's a significant, so I'm just stealing the question from part B because we were supposed to do it, but we're not. So is there evidence that there's a significant difference in the proportion of men who live in their parents' home compared to women? And then we're gonna test using a 99% confidence interval for the difference in proportion of men and women who live in their parents' home. Okay. So we just wanna know if there's a difference, right? Is there a significant difference? So I'm gonna steal this. Oops. Put it down here. See if I can. So we're not doing that. That's supposed to be blacked out. Looks like it's highlighted. Is there black? Still looks highlighted. All right. There we go. Yikes. So we want to know, is there evidence that there's a significant difference? So we don't care if one is less than the other, right? We just want to know, is there a difference between these two proportions of men who live in their parents' homes compared to women? So test using a 99% confidence interval for the difference in proportion of men and women who live in their parents' homes. So we still have to set up our null and alternative hypothesis, right? That's going to go for a formal hypothesis test or testing with a confidence interval, okay? And I don't know if I've mentioned before, but on the final, right? So before the final, I make you do a confidence interval and a hypothesis test, right? I made you do it on the test. I made you do it on the assignment. I keep making you do both of them, right? On the final, it'll only be one of them, right? So it'll be a question and then test using a confidence interval. Next question, different type. Here's a question, test using a formal hypothesis test, right? So it's not going to be nearly as long, I guess. It's going to be long-ish, but not as much work. Okay. So we want to know what's our null and alternative hypothesis. If we look at our formula sheet, you have the exact null and alternative hypothesis on your formula sheet, right? Because now we're comparing proportion of group 1 to the proportion of group 2. So our null hypothesis, and whenever we've got group 1 or group 2, it's nice to put little subscripts on our, at least our hypotheses, right? Because then it's easier to talk about the males and the females, right? So the proportion of males, we have to assume that it's the proportion equal to the proportion of females. So that's our starting point. We have to assume that they're the same until we have proof otherwise. Okay. Our alternative hypothesis is that the proportion of males is not equal to the proportion of females, because we just want to know if there's a difference between these two groups. So this makes it a two-sided test. I'm just kind of throwing you. Well, I'm going to call it the shallow end because you guys aren't new to confidence intervals, right? And you have the formula for the confidence intervals for two proportions, right? So let's jot it down and just make sure that we know everything that needs to go in there. There's nothing new there, right? And so we have our confidence interval is going to be our P1 hat. Remember, the hat on the P's make a sample proportion, right? Can't use bars anymore because bars mean that it's a sample mean, right? So we had to use something else, a sample proportion. So P1 hat minus P2 hat plus minus some Z star, which you already know how to find, right? Times the square root. Oops, what happened there? Disappeared. It was a Snapchat square root. P1 hat, Q1 hat over N1. So far, so good, right? As long as we remember that Q1 hat is 1 minus P1 hat, Q2 hat is 1 minus P2 hat. So, and then plus P2 hat, Q2 hat over N2. So let's jot down what we have. So for group 1, let's say group 1 is going to be the males. We have the number of successes. Which was, now I can't remember, 986. N1 was 2,253. Making P1 hat. Right? P1 hat is the number of successes in group 1 divided by N1. So in this case, our P1 hat is 986 divided by 2253. 0.4376387004. I think I'm okay with storing this, or do you want to round it? Let's round it. Let's use 3 decimal places at least though, right? 3 or 4 is good. So 0.4376. Round to 3 or 4 decimal places. If you want to round. Right? Okay. So what's Q1 hat then? Q1 hat is 1 minus P1 hat. It's going to be 1 minus 0.4376. Point 5624. So what's fun with proportions questions is that you only really needed this and this, right? Everything else kind of comes from there, right? And there's nothing else in your formula sheet except for group 2, right? But the same thing for group 2. So now we have to have the number of successes for group 2. And if you wanted to skip straight to plugging into the formula, that's fine, right? I just want to show you where everything's coming from, lay of the land. So group 2, let's say, is the females. The number of successes, oops, now I can't remember. Thank you. Save me some scrolling. 923. And 2. Thank you. That's all I need. So P2 hat is the number of successes in group 2 over N2, which is 923 over 2629. 923 over 2629. 0.35, I'll write out all the decimals first, 1084.062. I'll round it to 4 decimal places again, 0.3511. So Q2 hat must be 1 minus P2 hat, 1 minus 0.3511, 0.6489. Oh, cool. So really, we're comparing a sample proportion of 0.4376 to a sample proportion of 0.3511. Is there a significant difference in these proportions? When we take into account the different sample sizes, right, that has to be handled. All right. We need our Z star, right, because on our in our formula here, we just found P1 hat, P2 hat, done. Q1 hat, Q2 hat, done. We know N1, we know N2. So all we need now is our Z star, right, to tell us how wide our interval is. So our Z star, we use our trusty table, table C, and I think we want a 99% confidence interval. So a 99% confidence interval, if you zip down to the Z star line, you have a Z star of 2.576. So using table C, and I'm just explaining what I'm doing. Using table C with a confidence level of 99%, we find that Z star is 2.576. Right. Oh, because I told you here. So test using a 99% confidence interval. I'll have to give it to you, or I will always give it to you. The default confidence interval would be a 95% confidence interval. Just like we saw in the lab, that's the confidence interval that it spits out, but I'll always tell you what to use. All right. Ready, steady, go. I'll write out the blank formula again, right? So and then we can just fill it in. So P1 hat minus P2 hat. All right, we're testing the difference between these two groups, these proportions, plus minus Z star times the square root of P1 hat Q1 hat over N1 plus P2 hat Q2 hat over N2. Now it's just a matter of plug and chug. So P1 hat was 0.4376 minus P2 hat 0.3511. Plus minus Z star, which is 2.576 times the square root of, and here's where things get a little long, 0.4376 times 0.5624 over N1, which was 2253, right? Or was it 35? Awesome. Yeah. And then our P2 hat was 0.3511 times our Q2 hat 0.6489. Pretend that's on there. Shouldn't have been so lofty. Oops, not the same. Over N2, which was 2629, I think. Whew. All right. Nothing to it but to do it. 0.4376 minus 0.3511. I'll start there. We get 0.0865 plus minus, I'll leave the 2.576 till the end. In fact, I'll just simplify under the square root. Just to show you the steps, if you wanted to jump straight to whatever point, right? Show me just the plus minus, that's fine, right? Depending on how carried away you get in your calculations. 0.4376 times 0.5624, 0.2461064 divided by 2253. I'm going to store that in one. 0.3511 times 0.6489 is 0.22782879 over 2629. Store that in two. Recall 1 divided by 2253 point, and it's going to be small, 0.000109235 plus, store that 3, just as long as you keep track of where you're storing things. And like I said, if you don't know how to store stuff on your calculator, let me know. Yeah.
Could we leave a number like that inside the notation form?
Yeah, if you want to. Yeah. Fancy. Call 2 divided by 2629. 1, 2, 3, 4 zeros. 1, 2, 3, 4, 8, 6, 6. Repeating. Plus, recall 3. Oof, 2.576 times the square root of 0.000195895. Don't forget to take the square root. I see that all the time. 2.576 times 0.013996241, or you're a calculating machine, if you just skip to times 2.576 plus minus 0.036054318, that would be fine by me. But I do want to see what this amount here is, right? I want to see what this plus minus, this is the margin of error, right? So that's, I want to see. Okay. I'm going to store that for sure. And we've got 0.0865 all along here. Yeah. It's a skinny 8. How do we write our intervals? We use round brackets, right? And we have to do our lower bound first. So 0.0865 minus, I'll do recall 1. I get 0.050445682 up to 0.0865 plus recall 1 up to 0.122554318. Or if you wanted to just go to 2 or 4 decimal places, that's fine. How do we interpret this interval? So we have the same blurb for all these confidence intervals that we use. So we say that we are 99% confident the interval from 0.0504, right, or 5.04% if you prefer. Right. Proportions are nice. Proportions are percentages. Right. So if you want to convert them to percentages, that's fine. That the interval from 0.0504 to 0.1226 or 12.26% captures the difference in proportion, or in the proportion, I guess, in the proportion of males and females who live at home. Bless you. And hopefully I've basically just reused the question, right? The question said, use a 99% confidence interval for the difference in proportion of, men and women who live in their parents' home. Okay. So we're 99% confident that the interval from 5 to 12% essentially, right, captures the difference between these two groups. Zero's not in there, right? It's consistently higher than 0. If 0 was in there, then that would be the same as saying, well, the proportion of males must be essentially the same as the proportion of females, right? Because if this is true, then the males minus the females would be 0. Right? If they're the same, one minus the other is 0. Right? So we still look and see if the interval has 0 in it, then you don't have enough evidence to reject the null hypothesis. Because this interval is consistently over 0, right? Both values are positive. You have enough evidence to reject H0 and say that the proportion of males that live at home is different from the proportion of females who live at home. Nice. Oof. Since this interval is consistently above 0, above, and I'll just put above 0, we have enough evidence to reject H naught that the proportion of males equal to the proportion of females, right? Meaning that the proportion of males minus the proportion of females would be 0, right? That's the same, that's saying the same thing. And that's why we're comparing and looking at, is 0 in this interval? In favor of HA, saying that the proportion of males is not equal to the proportion of females. So there is evidence that what? The question said, is there evidence that there is a significant difference in the proportion of men who live in their parents' homes compared to women? You just reword that question as an answer, because now you know, right? There either is evidence or there is not evidence if you don't have enough evidence to reject H naught. So there is, yeah, I'll just copy this. I'm gonna be a cheater. So I can steal it. Oh. So there is evidence that there is a significant difference in the proportion of men who live in their parents' homes parents' homes, I guess, compared to women. We're just answering that question. Cool. Any questions about that? Great. Uh-oh. What do I do with 5 minutes? Let's just we'll just quickly start chapter 7. It's really fun, I promise. It's on scatter plots, lines of best fit. I promise. Chapter 7 is on regression.
We only have formulas for 7.2. 7.2 or 7.1?
7.1 and 7.2.
7.1 does not have any formulas then?
Yeah. So 7.1 is on correlation. You've probably heard the word correlation, even used it in just everyday stuff, right? A correlation is just, is there a relationship between two things? Okay? And so we're going to start with looking at a scatter plot. So we use a scatter plot we use a scatter plot to visualize the relationship between two numerical variables. So if you have something like this, here's your y-axis, here's your x-axis, right? Here's a beautiful scatter plot that we've made. It's more of a review from the first few classes, right? But on our y-axis, we have our response variable. And on our x-axis, we have our explanatory variable. Just like when I made you look at a histogram and describe the distribution, I'm going to make you describe the relationship between two variables. Okay, so to describe the relationship, there's another three things that we have to talk about. The first one is the shape. I like to use the shape because it reminds me of shape, center, spread, right? You can also call it the form. And the options are either linear, meaning it looks like it could be modeled by a straight line, right, which is what we'll be doing. Linear versus non-linear. Anything that looks kind of curved or S-shaped or kind of weird shaped, non-linear. The second thing we're going to talk about is the direction of the relationship. Options are positive or negative. Positive versus negative. A positive relationship looks like this. A negative relationship looks like this. So if it's going up, 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 positive. If it's going negative, all down, it's negative. And third, we talk about the strength. And our options are either strong or weak. Depending on what course you're in, there can be, 7 levels of strength. I just go strong or it's weak, okay? That will be a great start for next day. See you guys, well, either tomorrow or Friday or Monday. Can't get enough.